All right, so I'm going to start by answering a question about lab reports. Please remind me what it was. Oh, it was the how conversational the. Yeah, so in the lab report checklist, it talks about a few things to avoid so that you don't sound too informal. What were some of those things?
If you spill, bacon yeast, it'll be fine. That's all I know.
Yeah, so things like that. So if they give in their instructions in the lab report, like, or not in the lab report, if the instructions in the book for the experiment, they'll say a lot of things that are more conversational, like if you spill bacon yeast, it'll be fine. You don't have to include that. And really, like, you don't have to copy the procedure exactly from the book. You can, as long as, you know, if we did something different from the book, you do that different thing in the procedure as well. So if the book says, you know, I don't know, if the book says, like, set a timer for 10 minutes and we set a timer for 5, you know, you wouldn't write, we set a timer for 10 minutes because that would be inaccurate. You would do what we do in class. You would write what we do in class rather than what's in the book, although usually they'll be the same. Rory.
In the procedure, you mean like I mean?
Yeah, so it talks about, like, avoiding I, and Vale, you had your hand up, I think. Oh, sorry. And Bo.
Abbreviations.
Okay. Did it say? I think it did say something about abbreviations, right?
It said don't do abbreviations unless you have to.
Uh-huh. And anything else?
Should the procedure be told in past tense, like we did this, or should you do it like imperative, like do this?
Yeah, I believe what the lab report checklist says, if I remember correctly, is it says choose either. You can do it in present, and by that I think they mean the imperative, what you're talking about, or you can do it in past. We did this, or do this. So those are your two options, I believe.
But just be consistent.
Yeah, be consistent. And I'm going to double check that real quick just to make sure I'm not giving you inconsistent.
I think I have it. I don't think it's on the checklist.
Let me see.
Or maybe it's down in the, it's not at the formatting section. Writing in past or present tense.
Okay. Yeah, writing in past or present tense. So yeah, present is fine, and with that, I think they probably do mean what you said, the imperative, which is like command. You know, like do this, do this, do this. You know, whatever. All right. Yeah. So use concise technical writing with no slang. That's another thing. So you know, don't say something. This is a ridiculous example that nobody would say unless you're from Texas. You know, if the experiment didn't work, don't say, this experiment was all hat and no cattle, or something like that. I don't know.
Well, actually, I have a friend who speaks really southern, and so I had to understand what she's saying every time. Like, wait, what did you say again?
Does she use, like, weird expressions for things?
Sometimes.
If we ever have time to completely waste it in class, I have a video about Texas slang, which is kind of fun. But it's a British Korean guy teaching you Texas dialect. And so he's got a British Korean accent, and he's trying to do a Texan accent, and it's really funny.
Oh boy. I have to watch that.
But anyway, so what else? Yeah, use we and avoid you and I, because that's more informal to say you and I. And it says use scientific vocabulary throughout the report. I'm not really going to be checking for that, but just in general, like, you know, if there are terms, especially that we've defined in the background, don't be afraid to use them. And I think that was about it. Any other questions? The great thing about these lab reports is I can tell they're already making a lot of sense to you guys based on what you've been turning in, or what you've turned in so far, which is one. You know, I was impressed so far. But, you know, with practice, they just kind of become second nature. So it's hard at the beginning, but it gets easier toward the end. I do get a little stricter on grading things as time goes on, but you know, I'm still giving you comments on things that I would possibly take points off for, even now if I'm not taking points off for them. So something to note, just when I passed everything out a moment ago, I'm handling your headings this way. So remember we do like just the standard Libertas heading would be. I'm not going to do this every week. This is just since we're beginning. So first and last name. This is all like in the top right corner. Then physical science. And apparently I put this in the wrong order at one point, so sorry about that. And then the date, which would be, I don't know, let's say 27 August 2020. And I pointed out I'll also accept the MLA heading, but if you do that, it has to be like precise, or I'm just gonna like move everything over and turn it into this heading. So, but anyway, first and last name, subject. If this were a class with grade level, that would be included in there, but that's not needed for this class, and then the date. And so what I've been doing so far is just been taking off up to 3 points if you have a wrong heading. And so, you know, like if they're in the wrong order, that would be like 1 point. If they're, you know, if you're missing one of these things, that would be a point, and you know, things like that. So up to 3 points. Definitely make sure you have your names on everything that you turn in. That goes for every class. All right, everyone good? Let's dive into the material. Oh yes.
I have a question.
Yeah.
So is it okay if we write the date out in just numbers?
That's fine. Yeah. The reason I do this one is because this is what you would do if you were doing MLA, and so it's good practice for that. But you know, it's not the end of the world if you don't. I won't deduct points. All right. Very good question. So we are in module 2. So module 2, it's kind of interesting in this course. We'll cover basically like I believe it's 5 sections of the Earth, and those 5 sections are. You have one of them that we're covering right now, which is the atmosphere. And so the atmosphere is going to be like a body of air, you know, body of gases surrounding a planet. And then we're also going to do the hydrosphere, which is going to be all the water on the planet. And then later in one chapter, we're going to do one module, we're going to do the other ones, which are the crust, which is like the surface of the Earth, the mantle, which is an inner region, and then the core, which is the inmost region of the Earth. So this is one of the 5 regions of the Earth that we're doing. All right. So in the atmosphere.
I think you're in module 3.
Am I talking about? Yeah. Okay. So module 3 does that. I guess you're right. But a lot of this stuff is related to the atmosphere. So this isn't the one that's like the atmosphere module, but this is, you know, a lot of stuff that's related to it. So it's going to involve like the composition of gases in the atmosphere, for example, or at least the region of the atmosphere that we breathe. All right, so let's begin by talking about a concept. Well, I guess before that, I can ask this question: what is in the air around us? What's the air made out of?
Oxygen,
Oxygen,
and 1% of other things.
argon,
Uh-huh,
carbon
yep.
dioxide, ozone, sulfur oxides, and nitrogen oxides.
Very good. Yeah. So we have, and if you remember the percentages, I'm not going to look in the book for this, but I believe I can do it from memory. What is most of the air that we breathe?
Nitrogen.
Nitrogen. What percentage?
78%.
Good. So roughly a little more than 3/4. So 78%. N stands for nitrogen. That's the like chemical symbol for nitrogen. All right. And is any of this even visible on there? Probably not. There's a lot of glare. So I'll just say everything I write. Yeah, 78% nitrogen. And what percentage oxygen?
21%.
Very good. Okay, and so that leaves, if you have 78 plus 21, that's 99, so it leaves about 1% other. And Annalise mentioned that the main thing in that 1% other is what? You can repeat it if you want.
Argon.
Argon, yeah. And it also contains something we hear a lot about, which is carbon dioxide. And then it's just going to contain a lot of, you know, random pollutants that there's not very much of. And just other things like that, stuff that there's not too much of. But let's talk about why 78% nitrogen? Why is that important? What is nitrogen like as a chemical?
Isn't it like colorless, tasteless?
I think so.
Really affect?
It doesn't really do much, yeah. So that's the key to nitrogen. So it turns out that nitrogen doesn't really do very much. It's very much what we would call inert. So you know how when you cut an apple, very quickly it starts to turn brown? That's a process called oxidization. So when something oxidizes, it's reacting to oxygen. And it turns out, so oxygen's really reactive. And there's a few other things it does, including like it's needed in combustion, which we talked about in the experiment we did last class. But basically, if you had a whole bunch of oxygen in the atmosphere, it would do a lot of things that we don't necessarily want happening. So we do want a certain amount of oxygen because we need it to breathe. We need it for combustion. But the thing about oxygen, though, is if we had all oxygen, then basically you light a match and everything blows up. And then a lot of things would oxidize really quickly. So it's really important that most of the air around us is something that doesn't really do anything. We breathe it in, we breathe it out, we breathe in the nitrogen, we breathe it out, and it doesn't really affect us. It doesn't really react with our bodies, whereas oxygen does. All right, so we'll come back to this a little bit later, but I want to talk about how in the air we breathe. So this will be like the gases in the air, and there's going to also be varying degrees of, this proportion here will be mixed in with different amounts of water vapor. So tell me about water vapor. What is water vapor, just in a very simple sense?
Humidity.
Okay, good, yes. So it's going to be the humidity in the air. And is it a solid, liquid, or gas form of water?
Yeah.
Gas, good. When you boil, this is from another module, but if you boil, say, like salt water, here's a bunch of like salt water, and if you boil it, then what gets evaporated? What goes into the atmosphere out of the salt water? Is it going to be the salt and the water, or just the water?
Water.
Just the water, yes. And when it does, we did electrolysis before in our first experiment, and what we did there is we actually split up water into hydrogen and oxygen. But that's not what happens when water, like say, ocean water or lake water or whatever, when those things evaporate and become water vapor, what's happening, I guess I didn't need to erase that yet, is the water molecules, they're getting spaced farther and farther apart until they're thinned out so much that they can actually go into the air. They break apart from each other and they become water vapor. So the steam that you see, the water molecules are still hydrogen and oxygen bound together. They're still molecules, but they're spread so far apart that they go from a liquid to a gas and they can rise upward, especially because they're hot. So yeah, water molecules make up water vapor. And water vapor will get mixed in with the air around us. We constantly have tons and tons and tons of water vapor being evaporated from, especially the oceans. So we'll talk about humidity real quick. What is humidity? And the definition of humidity is the moisture content of air. Somebody can double check that for me real quick. I believe that is correct. The moisture, you're faster than I am.
Absolute humidity or relative humidity?
Humidity in general.
I don't think there's a... Oh, here it is. The moisture content of air.
Perfect, thank you. Okay, good. So, yeah, so this is just basically when you say what is the humidity, you're saying how much water is in the air, and it's going to be water vapor. How much water vapor is in the air when you're asking about humidity. Now, can water be in the atmosphere in other forms?
Yes.
Yeah, like when it gets really high, then it'll freeze into ice. We'll learn later that that's like what cirrus clouds are made of. The really high wispy clouds are made of ice. And of course, when precipitation occurs, that's when the water vapor comes together because it cools and comes down as either a liquid in the form of rain, or come down as ice in the form of like hail or snow. Or but when we're talking about humidity, we're saying like how much water vapor is in the air. All right, and there's something called a heat index.
It's a combination of temperature and humidity.
Very good. This is going to be a combination of temperature and humidity, and it's designed to tell you not how hot it is outside, but how hot it feels. So if you have, I don't know, let's say it's 100 degrees Fahrenheit, and it's really, really dry, which you guys have probably never experienced living in Tallahassee, like dry heat. let's say, okay, so situation A, 100 degrees and it's really dry. Situation B, 100 degrees and there's a lot of water in the atmosphere. Which one's going to feel hotter? A or B?
Can you repeat that again?
So A is going to be like there's not a lot of humidity, there's not a lot of water vapor in the atmosphere, and then
Second one.
yeah, so it'll be B, where if you have a high humidity and for any given temperature, like the more humid it is, the hotter it'll feel. So the temperature in situation A, if there's like no, not really any humidity, let's just say that the heat index is like 100 degrees. But in situation B, when the temperature is 100 degrees, if there's a high humidity, it might feel like 113 or something like that. So your heat index could be 113. Your body actually has a way of dealing with heat, which is sweat. How many of you here, like, you hear the word sweat and you just kind of go, ugh, inside? I don't know. I'm curious. I bet a decent percentage of people, that's their reaction. But what's actually happening when you sweat is, here's a person, and I'll just like focus on their head. So they're experiencing a lot of heat. So they're kind of sad or perturbed. And in the heat, what happens is you'll start to sweat, so water, you'll start like secreting water mixed with other stuff.
Beautiful.
There you go. And then what happens to the sweat?
It evaporates.
It evaporates, yeah. So when it evaporates, what's happening is the heat in your body is being spent, it's being used up, it's transferring to the water. And if it just stayed there, it wouldn't really cool you down that much because the water would be trapping your heat and just sitting on top of you. So that wouldn't really help that much.
Unless it's like
But
the
it makes
humidity is
it worse.
really, really hot, it might
Yeah.
go like completely quickly.
And so if though the heat goes to the water, what it'll do is when you heat water up, it evaporates. It goes from a liquid to a gas, it becomes water vapor. So then your sweat, whether you know it or not, is actually evaporating. And so the heat in your body goes into the sweat and then the sweat goes away. Not everything in the sweat, but the water in the sweat goes away, and it actually spends that heat, so it cools you down. But if it's a really, really hot, I shouldn't say a really hot day, a humid and hot day, then what can happen is if there's too much moisture in the atmosphere, then think of the atmosphere as like a sponge, all right? For any given temperature, it can contain a certain amount of water vapor. Just like a sponge, you can like dip it in water and it'll bring out a certain amount of water that you can wring out. So if the atmosphere contains so much water vapor that it can't easily take in more, like that sponge of the atmosphere is almost full, then what happens to your sweat?
Sticks on you.
Yeah, it's not going to evaporate so fast, and might not even evaporate at all. And so in that case, all the heat that was getting spent to evaporate your sweat instead just stays in the sweat, and the sweat just covers you. And so you just kind of stay hot. I guess you'd still probably feel a little better with the sweat than without. And I
That
suppose you
might
can always
feel
just
bad
like
here
do
in
that,
Florida.
especially
Yeah.
me. I can just like do that and get all the sweat off my head. And then more would come. But
Yes,
anyway,
exercise outside in the morning in Florida.
yes, definitely.
Mr. Nicholson, are you live or just recording?
Just recording. If you are actually if anybody wants to get into the Zoom room, so the thing is the internet was down this morning, it's still down. So I sent an email out about this last night, but just in general, if you ever can't get in, don't worry, just know that I'm going to, that I'm doing a recording myself, and we'll post it later, like on YouTube or something. So think about my YouTube videos, let me know if you are ever like, no, I absolutely don't want my student in the class that goes on YouTube. But what I'm doing is I'm not tagging them so no one can find them, basically. So like you would have to actually go into my channel and be like, hey, look at this class, and click on it. You can't actually find them. Except by the title, I guess, but that's not really going to get any results. I can also make the videos like, private or whatever. But right now it's the setting that I think will be the easiest for you to just use the links. But I don't think anybody will ever find them by searching. So let me know if you have any problems with that, but I think it's the best solution for now, and I can certainly adapt it if I need to. So anyway, and of course, first thing I'll always try to do is the Zoom room, but just if for some reason like today it doesn't work, or like last week it didn't work, you know, and some of the things going on, by the way, with Zoom, I'm hearing about how like basically there's so many people across the world using Zoom right now that school has resumed, like there's kind of a pun, resumed, but there's so many people using Zoom accounts that like, you know, people are just getting booted out because their infrastructure can't handle it. And that was what was happening to me last week, I think. So just bear with it and know that the Zoom Corporation will probably fix that. But that's really out of our hands. So this is my backup plan going on. All right. So the good news is we have backup plans. So we make it work one way or the other. All right, so we need to talk about two types of humidity, and I've already hit on it a little bit. This is something that's like one of the harder things to get in this module. It's not super hard, but people sometimes get confused by it. So the first one is
humidity.
very good. Yes, absolute humidity. I'll just say this: two types. Absolute humidity. Can somebody read the definition of that for me, please?
The mass of water vapor contained in the same volume as air.
Great, thank you. I'll say H2O, vapor, contained in a certain volume of air. So this would be like how much water is in the air, period. Like, just pretend you have, and I'm not gonna make even even remotely realistic numbers here, but just let's say that you got a great big thermos. I don't really care how big the thermos is, but that's your thermos. And you put it over like a tea kettle, and you just catch all of the steam in the tea kettle. Then the absolute humidity, like let's say then you close it, and you just got like a lot of water vapor trapped in there. So the absolute humidity would be like there are, I don't know, 10 grams of water in that thermos. Does that make sense? Because that would be like if you were to take all that water vapor and weigh it, then that would be like your absolute humidity amount. So it's how much actual water, like what's the mass of water, and grams measures mass, remember? So when I said weigh, I mean weighing the mass. That's going to be your absolute humidity. Yes, Bo? Sure. So any questions about absolute humidity? Okay. So I'm just going to make up the absolute humidity. Let's say it's 10 grams of water. Now the other type is called relative humidity. And I think this one's a much longer definition, if I recall. So maybe I should move it over here. What is relative humidity? Somebody read that.
The ratio of the mass of water vapor in the air at a given temperature to the maximum mass of water vapor the air could hold at the temperature, expressed as a percentage.
Great. I'll ask you to read that again, because I only got the ratio of.
Oh, sorry.
No, you're good.
The mass of water vapor in the air at a given temperature.
Okay, pause for a second. I still not have enough room.
No, there's a lot more.
All right, continue, please.
To the maximum mass.
I'm gonna just continue over here. Maximum mass
Of water vapor. The air could hold at that temperature.
say temp for temperature.
comma, expressed as a percentage.
Very good. Expressed as a percentage. You probably can't read all the way down here, but whatever. Sorry for those of you watching at home. I know the board's not very visible. There's a lot of glare in this classroom. Okay. So that's quite a mouthful. The ratio of the mass of water vapor in the air at a given temperature to the maximum mass of water vapor the air could hold at that temperature expressed as a percentage. So there's a few parts of this. So first of all, it's a ratio. And what is a ratio? Like, what's another name for a ratio? Very good, a fraction. Yes, so a ratio is a fraction. You're saying this much out of this much. So is a percent a ratio? Yeah, so if I say 10%, that's the same thing as saying 10 out of 100, right? So when they say that this is a ratio expressed as as a percentage, a percentage is a ratio. It's just a certain way of saying it. Oops, wow, that marker just went under the stage. Didn't realize there was a crack there. So there might be 10 grams of water vapor in this thermos. But let's say, what temperature should the atmosphere in the thermos be?
50.
Okay, so let's say that it's, I'm not gonna say it's like 50 Celsius, I guess. I don't need to put that there, I'll put it above. So this thermos is 50 degrees Celsius. So it's pretty hot, it's like halfway to boiling. So that would be like, you know, about 106 degrees Fahrenheit. And so let's say that at 50 degrees Celsius, the absolute maximum amount of water vapor that this thing could hold, before it becomes a bunch of water droplets, like let's say that that you couldn't put any more than I don't know, 20 grams of maximum humidity in there. So like, in other words, if your absolute humidity is 10 grams, meaning you got 10 grams of water vapor in there, and you could actually take in a total of 20 grams of water vapor before it just becomes water rather than vapor, then what would your relative humidity be? It's a ratio of the amount of water, so 10 grams, compared to the maximum amount it could hold at that temperature, so 20 grams. If you divide 10 by 20, then what percent do you get?
1/2.
Yeah, 1/2. So this is 1/2.
You just take zeros out.
Yep, and so that would be 50% relative humidity. So the absolute humidity is 10 grams, but the relative humidity is 50%. So 50% humidity means that you're 50% of the way to holding the maximum amount of water vapor that you could possibly hold at that temperature. Does that make sense? So let's say instead you get a little bit more water in there and it's 15 grams. What would the relative humidity become? It's still 50 degrees Celsius, so it can hold a maximum of how many grams? 20, good. So now our ratio is 15 out of 20 because we have 15 grams in there, and we got 20 grams that it can possibly hold. So what's 15 divided by 20 as a percentage?
75%.
Very good. So we'll reduce this. So if these are both divisible by 5, so 5 goes into 15 3 times, it goes into 24 times. 3/4. If you divide 3 by 4, it becomes 75%. Or it becomes 0.75, which is 75%. All right, now let's do something different. Let's say that you increase the temperature. So I'm going to say 75 degrees Celsius. And at 75 degrees Celsius, when the air gets hotter, do you think it can hold more or less water vapor? More. Yeah, it'll actually be more. So let's say now that at 75 degrees Celsius, you could hold up to 30 grams of water vapor in this thermos. All right? So if I still have 15 grams of absolute humidity, meaning there's 15 grams of water vapor in there, then what is my Valen Bo? What is my relative humidity? 50%, yeah, because now I've got 15 grams, but I can hold a total of 30 grams. And so I can hold 1/2 of the total amount, you know, that is possible to, like I have 1/2 of the water vapor that I could possibly hold, 1/2 of the humidity. So if you divide these, they're both divisible by 15, so 15 divided by 15 is 1, 30 divided by 15 is 2, 1/2 is 0.5, which is the same as 50%. So yeah, now our relative humidity is back to 50%. All right, any questions about this? Quick recap then. I say the humidity is 31 grams in this thermos. Is that an expression of absolute humidity or relative humidity? Very good, yeah, so if the measure is like a quantity, it's gonna be absolute humidity. But if I say instead it's 45%, then what type of humidity is that? Relative good. So if it's expressed as a percent, that's going to be relative humidity. All right, so hopefully everyone's good with that. And at what point does water not actually get dissolved into the air at all, or like evaporated into the air at all? When is evaporation impossible? Like when would you not sweat at all? That would be when the relative humidity is 100%. Which means, again, it's a ratio of the mass of water vapor in the air to the maximum amount that's possible for the air to hold at that temperature. So if you could have a maximum of 30 grams of water vapor in this thermos, and you have 30 grams of water vapor in this thermos, then if you were to put this thermos over some hot water, that hot water would not evaporate because the air is full. So it can't take any more water. Does that make sense? Or in the same way, if you're outside in 100% humidity, you're going to sweat, but it's not going to evaporate. You're just going to get soaked. And yeah, I know a lot about human environments. I did a total of 10 weeks across 2 different mission trips in Cambodia. And that is very, very, very humid in that part of the world. So, and I was there like during the rainy season. And that's like, I've heard someone describe that part of the world as like during the rainy season you have like rain o'clock every day, which is sometime around like, you know, maybe 11 a.m. to 2 p.m. Like it always rains every single day. Just constant, like crazy high humidity, just pouring sweat all the time. It was funny because one day like, it was just a little bit cooler and it was probably still like close to 80 degrees. But like there was this girl who was wearing a hoodie and she was shivering. And she asked me like, "Aren't you cold?" And I just laughed at her. But that's just what they're used to. It might have been like the mid-70s, but anyway.
So relative humidity explains why our humidity is lower in the winter.
Actually, that would be true as well. Yes, because when it's colder, you can't.
Hold less water vapor.
Exactly. Yeah, that's very good. So yeah, wherever it's colder, you're going to have a lower like amount of humidity that like you're going to have a lower amount of water that can be absorbed into the air. All right, so that term, by the way, one last thing. So if someone says saturated, when referring to humidity, what they mean is that you have 100% relative humidity. So you can't take any more water vapor into the atmosphere. It's like if the atmosphere where you are is like a sponge, it's like that sponge is totally full. You stick it in a jar of water or a bowl of water, whatever, and bring it back up, and it doesn't have any more water in it than when you first put it in because it just can't take any more. It's totally saturated. All right. Moving on. Dang, class is like, there's 15 minutes left. All right, the composition of air, we've already talked about it. So the composition of air, meaning like, what's it all made of? 21% oxygen, 78% nitrogen, 1% other. And oxygen, we mentioned before, is required in combustion. So remind me what combustion is?
Burning.
Great, burning. And how does it relate to our bodies?
Well, we need it to breathe.
Yeah. So our bodies are actually run by a process of combustion. So what you need for combustion is you need oxygen plus a fuel, and then it needs to be burned. So same thing with your cars. Like, you actually need oxygen to be able to get to your engines. I guess to your engines, right? In order for your cars to run on gasoline. So gasoline is the fuel, and then you add oxygen, and then you can burn. Take a force, like let's just take a campfire. What is your fuel in a campfire?
Wood.
Wood, good. So you take the wood, you need oxygen. How many of you know that if you cover a campfire, then it goes out because you're taking the oxygen out of it? Just like in that experiment where we put the jar over the one candle and didn't add oxygen, the candle just went out really quickly. So, and in the case of our bodies, what is our fuel for the combustion process? And what form of energy? Yeah, food. So when we eat, we take in calories and we burn the calories. Like, we literally burn them. That's not just an expression. And we can do that because we are combining, our body's taking in the food, and it's also taking in oxygen through our lungs. So when you die from suffocation or anything like that, what that is basically you're not taking in enough oxygen to power your brain. Is kind of like the thing that's going to cause you to black out, eventually not enough for any of your systems. So, all right. And it's interesting too because we have exactly the right amount of oxygen. If we had too much, it would cause lung damage or blindness possibly. And if you had 22% oxygen, in other words, you went up just one time, like 1% of the amount of oxygen in our realm of the atmosphere. There's different layers, but in our layer, which is called the troposphere, then you would actually have 70% more chance of forest fires. So if we had 22% oxygen, then there would be 70% more forest fires in the world. Isn't that crazy? Just that little bit. How is oxygen produced?
Plants.
Yeah, so plants, and also something that people overlook but produces a huge amount of the oxygen on the Earth.
Yeah, it's like something that they like.
Yeah.
Is it phytoplankton?
It'll be algae, yeah. And so I can't remember exactly. Phytoplankton's an animal, right?
Yeah, I think so.
Does it photosynthesize? I can't remember.
Not what I ate photosynthesized.
But yeah, so algae will produce a huge amount of the oxygen in the world. So and then when we breathe out, what's one of the byproducts that we create?
Carbon dioxide.
Carbon dioxide, right. And what do algae and plants who produce oxygen need? Carbon dioxide, yes. So and any time that combustion occurs, carbon dioxide will be given off as a byproduct. And also, water is another thing. So believe it or not, water is given off. And that's perfect because plants need both of these things. So that works out. It's a good cycle. Now, carbon dioxide, and I guess before I get here, I'm going to skip ahead. I'm going to do this in the wrong order. Look at page 35. And this is a picture of the composition of air normally, and then the composition of the air we exhale.
2.5.
Yeah, figure 2.5. All right, so inhaled air has what percent oxygen?
20%.
Yeah, 21%. Exhaled air, it actually goes down to what percent?
16%.
Good. So we only use out of all the air we breathe in, we only use 5% of it as the oxygen that we actually take in and utilize. And so, and you can look at it this way. I mean, you're using approximately a quarter of the oxygen you breathe in, and the rest, 3/4 of it, just gets breathed right back out. Your lungs are really efficient at absorbing oxygen, but you know they're not like 100% efficient. So, and then 4% of the air that you breathe out is carbon dioxide, and 4% is water vapor. Because remember, both of those things are byproducts of combustion. So you ever notice how, like, when you breathe out, like the air that you breathe out is more moist than the air you breathe in? That's going to be part of the reason. It's because of combustion going on. All right, so I'm not going to put that on the board, but just remember the air you breathe out would be 16% oxygen, 4% carbon dioxide, 4% water vapor. All right. Now let's talk about greenhouse gases and global warming. First, they define something called, well, I think I won't go there yet. Yeah, so greenhouse gases.
Is that the greenhouse effect?
Mm-hmm. They're gases that will cause the greenhouse effect, yes. That's very good. So how do you define greenhouse gases anyway?
It has to do something with the ultraviolet rays from the sun.
It does. Although actually in the case of, now one of the greenhouse gases directly does, and that's ozone. And all the greenhouse gases will relate to something called infrared light, which we'll get to in a moment. So greenhouse gases. The basic idea, this is not the book's definition, is these are going to be gases that trap heat from the sun that reflects off the earth. So here is the earth. Here is the sun.
Why is he so mean like
I don't know.
So that's just some ultraviolet rays.
that? Did he lie a bunch?
Yeah, it looks like it. So, so the sun is always giving off, you know, different types of light. Our visible light actually contains a lot of different types of what's called electromagnetic rays, and some of them we see. That's going to be visible light, like all the colors in the rainbow that we can see. But there's also, if you have something that's redder than red, that's going to be light to the point where we can't see it. That's going to be infrared light. And infrared light is actually going to be heat. So from the sun, there's UV light, there's infrared light, there's the visible spectrum, there's a bunch of stuff traveling to the earth. And here's our atmosphere. Let's see if I can find the image of this.
It's on the other page.
Oh, perfect, thank you. Yeah, so the light coming from the sun is going to, some of it will just bounce off of our atmosphere and reflect back into space. But some of it will make it through and hit the earth. Then when it hits the earth, some of it will bounce back off too. But as it's bouncing off, then this radiated light that's bouncing off the earth has an opportunity to be captured, specifically the infrared portion, the heat portion, has an opportunity to be captured by greenhouse gases. Those greenhouse gases are going to trap the heat from the sunlight before it radiates off of the earth and back into space. Does that make sense? Or back towards space. So it turns out then that the earth is only as warm as it is because we have certain gases in our atmosphere. And so those gases are going to include the following. Carbon dioxide, which again, anytime there's burning, so like anytime you're burning coal or fossil fuels or pretty much anything, like carbon dioxide is going to go into the atmosphere.
Methane.
Yep, methane. this is marginally homeschool appropriate. No, that's a saying that my sister and I have is it homeschool appropriate? But so methane is actually like a very potent greenhouse gas. It'll trap a lot of heat. And did you know that people who are concerned about global warming are concerned about the number of cows in the world?
Yeah, still with their farts.
Exactly. I wasn't going to say it like that, but yes.
Leave it to the.
Yeah, methane. Water vapor is one. So water vapor, and that's probably not a surprise, it'll trap heat. And then ozone. Ozone has another role, which we'll talk about later, but that has to do with catching UV light and neutralizing it so that we're not like fried by ultraviolet radiation. So ozone is very helpful in a couple ways. You just don't want to breathe it. Just remember that. All right, so those are greenhouse gases. And the greenhouse effect is not the gases themselves, but I think someone could read the definition of the greenhouse effect, right? Please do if you have it.
The process by which certain gases, principally water vapors, carbon dioxide, and methane, trap heat that radiates from the earth.
Yep, good. So this is the process by which greenhouse gases, I'm not going to list them all right now, I'm shortening the definition because I already have them listed here. And I'll just say trap heat, and that's going to be my short version because I already explained the rest in here. So the gases are carbon dioxide, methane, water vapor, ozone. The process is the greenhouse effect. So when they keep heat in the atmosphere, warming the earth, that is called the greenhouse effect. Now, is the greenhouse effect good or bad?
Good.
It's good. We would die without it. What happens if you have too much of it and it becomes a bad thing? What do you call that?
Ozone greenhouse?
Nope, not that, but good guess.
Too much greenhouse effect.
Yeah, too much greenhouse effect. What do we call it?
Toxic.
That would be a good adjective to describe, something harmful, yeah. But the particular term, and you've heard this term before, you'll probably groan when I say it, because you've heard it before. People are like, why didn't I think of that? Global warming. So, yep, I was right. Okay, so global warming is basically too much of a good thing. It's too much of a greenhouse effect. So we don't want too little
No, too much.
of these gases, but we don't want too much either. The book will say a lot of interesting things about global warming, including just the fact that, our man-made sources of all these gases are, they're relatively small compared to, natural sources of it. And it's really interesting because when a volcano erupts, it produces tons and tons and tons of greenhouse gases. It's same with forest fires, and they'll talk about the actual data of Earth warming or cooling over time. And so there's a lot of good counter-arguments for global warming that they go over. But you can form your own opinions on whether or not you think it's a real threat at this point in history or not. We have covered the composition of air, greenhouse gases, global warming. We need to talk a little bit about ozone. And I think that's probably a good place to end today, and then we'll get into the rest later. Maybe I can hit this too real fast. So yeah, I'll do ozone first, okay. The ozone layer is somewhere in the atmosphere. It's actually right at the bottom of what's called the stratosphere. So it's higher than the weather, than most weather that goes on. It's certainly higher than the air we breathe. But the ozone layer is made up of ozone molecules. It's not like they're thickly packed or anything. They're still spread far apart. I'm drawing them like this without the normal chemical bonds for a reason. Not because this is accurate, but just to get an idea across. So remember, the sun is radiating a lot of different things, including ultraviolet light. I'll just finish a couple sentences. And the UV light that the sun gives off, it's high energy, all right? And so if it strikes your cells, it's so high energy it'll kill them. But if it hits one of these ozone molecules, imagine it's like playing pool. Like the UV light is like the cue ball, and when it hits, it's going to break apart the ozone molecule. But the energy is going to be spent, so that cue ball is just pure energy. It's not mass. So imagine the energy of a rolling cue ball, but then when it stops, the cue ball disappears. That's basically what the UV light does. It spends itself and vanishes when it hits an ozone molecule. So that's how the ozone molecules protect the Earth from UV light. Okay, thanks very much. We'll pick up, and we already covered almost everything in the module, but we'll hit what we didn't cover next class. Have a good lunch.